Hello, I'm Pablo, and I'm presenting here my work, which is assessing the power of artificial intelligence approaches for bird model classification. So, studying diversification is a real complicated task since we need to infer process that generally occurred million years ago. At first, they tried to study diversification with the fossil record, but this is problematic because, as we know, for most of the extant groups, the fossil record is sparse. So data phylogenetic trees contain information about past evolutionary events in the branch length distribution and topology. Because of this, they have been proposed as a primary data to conduct diversification studies. Those phylogenetic trees are often represented with lineage through time plots, which consist in a curve that describes the accumulation of star lineages over time. The diversification studies carried out with those phylogenetic trees are generally done with bird models, which are a stochastic branching process that describe how the number of species change through time. This model had two main components: the speciation rate, which controls the tempo of emergence of new species, and the extinction rate, which controls the tempo of elimination of species. Also, a third parameter, known as the sampling fraction, is often included just to account to the fact that not all the extant taxa are included in the phylogeny. So two indirect parameters, the diversification rate, which is the speciation minus the extinction, and the relative extinction rate, which is the ratio of extinction to speciation, are also used. The likelihood density of those a constant bird model applied to a phylogeny was first derived by Nian collaborators in 1994. They say that in the past, the lineages accumulate with a diversification rate, which is speciation minus extinction. But in the recent past, this diversification rate is only defined with speciation, because lineages have no time to go extinct. So this change in the slope is why they call it pool of the present, and allow us to estimate speciation rate and extinction rate separately, but just for bird constant models. From this starting point, more complicated models have been developed. So when rates vary through time, they are denoted as time-dependent models, and they can be continuous or discrete. Also, when the rates vary through the different lineages, they are denoted as clade-dependent models, and they can be lineage-dependent models or trait-dependent models. Where rates vary with environmental factors or biotic factors, they are denoted as environmental-dependent models or diversity-dependent models. Some of the models explained before have some identifiability issues. That is, they have parameters which are non-identifiable. There are two types of non-identifiability. The structural non-identifiability is when given a set of parameter values, they induce the same likelihood distribution, identical. And the practical non-identifiability is when given a set of parameter values, they induce likelihood surfaces which are difficult to differentiate. So this second type, in this second type, increasing the data may improve this identifiability, and it's also related with computational intractability, when the likelihood surfaces which are flat or have multiple optima are difficult to differentiate and hamper the parameter estimation. One example of this non-identifiability was proposed by Tanja Stadler for discrete redshift models. So she compared a constant bird model with a mass extinction event discrete at a time t, and a model where the rates, the diversification rates, change in a discrete form. And she noticed that they generate the same entity plot, so you can differentiate among them. Also, Stylianos Loca and Matthew Pennell in 2020 demonstrated that continuous time-dependent models generate non-identifiable deterministic LTT plots. That is, different combination of parameter values for the speciation rate and the extinction rates generate the same identical diversification trajectories. All of these trajectories were said to belong to the same congruence class. So to try to solve all of these identifiability problems, there have been different solutions proposed by different authors. So one of the solutions will be the hypothesis-driven exploration, which consists in constraining the model selection to a given set of models based on prior biological knowledge. Also, you can try to constrain the parameter estimation. This can be done just by fixing one or several parameters in the model, or with estimating one parameter in the model and marginalizing over the other with Bayesian inference. Also, you can try to do Bayesian regularization. And the last solution, it will be to embrace the uncertainty that consists in explore the different diversification trajectories among a congruent class and try to establish difference among them. It is also important to say that in 2022, some authors demonstrated that piecewise Bader models, which are a type of discrete recessive Bader models, are identifiable as long as you have a big enough phylogenetic tree and some knowledge of the present day population. In this work, I'm trying to study the identifiability of some models that have been problematic in the past. Specifically, I have like three Verdex constant models, one with the relative extinction, the natural relative extinction based on the fossil record, which is the constant Verdex, another with a high relative extinction, which is the high extinction, and another constant Verdex model interrupted by a mass extinction event in a discrete time. And we compare these models also to rate variable models. The diversity-dependent one, in which the speciation rates decrease exponentially with the number of lineages, and two discrete rate models. One in which after a discrete time, the diversification declines, which is the Wasserman-Waning model, and another with after a discrete time, the diversification rates start increasing. So in order to do that, I used a supervised machine learning approach. Specifically, I used convolutional neural networks. And I tried to solve two types of problems. A classification problem among the different scenarios that I have explained before, and a regression problem, which consists in estimating the diversification rates of all the scenarios that I have explained. So the first part was to design our dataset. It was clearly the most hard part because defining the parameter range for each model was very difficult. We did that in the R package 3sim. And at first, we only constrain our phylogenies to the number of lineages. But we found out for the discrete recessive models and for the mass extinction models, this package often generates trees that are shorter than the time t at which the discrete event must occur. So, for example, this was supposed to be a mass extinction, but as we can see here, there is no mass extinction event here. So we needed to fix that, and in order to do that, we also constrained it by the crown age. So we say to the algorithm that only those trees in which the crown age was 5 million years older than the model discrete time event were annotating. So applying this dynamic filter, we were able to simulate the models that we wanted to do. We simulated a total of 100,000 trees for each diversification model. We did that with the diversification and the relative extinction parameters sampled from uniform distributions. Also, all of trees have 492 tips, and our sampling at present was 100%. We did that in order to make our simulation dataset as close as possible as to our empirical case, which is the phylogeny of conifers published by Leslie and collaborators in 2012. One extension to this was the Washington model, because simulation were so time consuming, so we were only able to simulate 10,000 simulation instead of 100,000. Also, we performed a regular PCA just to check that the parameter values of our empirical phylogeny falls within the distribution of our simulated dataset. Once we did that, we need a form to perform optimal input for our neural networks. So I'm not going to explain this again. I think that you have heard it enough. So at first, Botnik and collaborators in 2022 developed this representation for non-ultrametric trees. Then Lambert and collaborators in 2023 readapted this representation for ultrametric trees, binary state speciation and extinction models. And what we did was to readapt this vectorization to our case. So we have no tip state. So what we did was to take out the tip state from the vector, and our vector is only defined with the distance of each node to the root and the total tree of the total height of the tree. We also take out the sampling fraction, because as we assume that it is 100% for all of our phylogenetic trees, we didn't consider it. Here we see the workflow that we follow with for our training design. So each vectorized tree of the different scenarios was used to train one classification model in order to classify the different scenarios, and also the parameters used for the simulation and the encoded trees of each scenario was used to train 5 regression models, one for each diversification scenario. So the idea is that once that all the models have been trained, you just have to use your empirical phylogeny into the classification model, and depending on this classification, your phylogeny will be sent to a different regression model, which is specified for this diversification scenario, and will estimate the diversification parameters of that scenario. And here I will present our results. For classification, we try a model with 10,000 simulations, just because we could include the Washington 1-in-1. And as we can see here, the accuracy was almost 90%. And the most confused model was the mass extinction one, and it often gets more confused with high extinction, and followed by stasis and radiate, which makes sense because tree topologies in these models are pretty similar, and our vectorization is just representative of the length of the different branches, so makes sense. Anyway, it is a high accuracy for the little difference that exists on these trees. We also trained a classification model with 100,000 simulations, and our general accuracy was almost the same, 90% almost. So there is no difference between increasing the dataset size. For our regression results, and for the Verdes constant models, we got higher. We expressed the mean absolute error. As we can see here, it is higher for the relative extinction rates than for the diversification rate. Also, as we can see here, especially in the relative extinction, our median and our mean are pretty different, and this is because of our confidence intervals are biased towards some higher values that we think that might could be rare phylogenies or rare trees, and this is why this is happening. For our RACIF models, we again see higher errors for the relative extinction rate than for the diversification rate, and the diversification rate have more precision when it is estimated in the past. It is before the RACIF event, and the precision is lower when it is estimated after the RACIF event. And for the relative extinction is the opposite. Also, as we can see here, the error in the time is the biggest one, but it is just because it is expressed as an absolute value. So as time is bigger number, so it's also bigger error. For mass extinction model, again, we see that the diversification rates are more accurate than the relative extinction. And it is curious that our error in the moment of the mass extinction is higher than the error to detect this RACIF. So we think that with these two representation, it might be harder to detect the moment when a mass extinction event happens than to detect the moment when this RACIF is happening. For the Watson and Waring model, we could not perform this analysis because we don't have enough simulations. So we are looking forward to a new simulator in order to be able to estimate the rates. And our empirical case was classified with 70% as an ecstasis and radial model, and with almost a 30% with a high extinction model. And those were all diversification parameter values. As conclusion, we can say that Verde's model suffers from identifiability issues. Also, that we explore here the power of supervised machine learning, CNN, to discriminate between alternative rate constant and rate variable models. Classification accuracy and precision values were high for each model, circa 90% and 80%. And regression analysis was successful with mean absolute errors below 0.5 for the diversification parameters. Also, when we applied this algorithm to our empirical case, it fits as an ecstasis and radiate as the best model, with an increase in diversification rates close to the present. The second best scenario is high extinction. And this result is consistent with the fossil record, which says that some groups in the conifers are suffering like a radiant moment right now, and other groups have been exposed to high extinction over the time. So we need to check this, but we think that our CNN is able to predict different diversification scenarios in the same tree. But we need to check this because I did this just a week later, so I have no time to check this. And thanks to my research team, and also to all the staff of my research center who have supported us in this journey. Thank you very much.